Yeah, so I am going to talk about flux inversion a little bit, and basically something that we've been trying to do to help improve flux inversion modeling from the perspective of the atmospheric transport model. Yeah, and this is joint work with my supervisors, Dr. Andrew Zamit Manjan and Dr. Nicholas Deutscher. So I'm going to talk about methane. It's the second most prevalent anthropogenic greenhouse gas in the atmosphere. It's second to carbon dioxide. However, the ability of methane to actually trap heat in the atmosphere is about 30 times more effective than carbon dioxide. So, it's quite damaging to the, I don't know, or it contributes a lot to the global warming effect that we're seeing. And, the really concerning thing is that the levels of atmospheric methane are, just continuing to rise. And look, we're quite good at actually measuring that atmospheric methane, but quantifying those measurements is still quite a difficult thing to do. So, when I say quantifying, I mean, taking those measurements and saying, well, where did they come from? How much came from what location? Was it contributed by human things, like industry, etc., or was it contributed by natural effects, etc.? So, working out where it came from. Okay, and that's where flux inversion comes in. So this has been done a lot, flux inversion is used quite a lot to quantify greenhouse gases. And I've just listed some of the recent examples here. It's, by no means an exhaustive list at all. But just to give you an idea about, how broad it is. So the basic idea behind flux inversion, if you're not familiar, is that you would have a collection of observations. So these would be measurements of methane, around whatever domain you're interested in. And then you would choose an atmospheric transport model, and you would use that to simulate those same measurements. And then basically you adjust the parameters of your atmospheric transport model so that the modeled concentrations and the observations that you have match up as best as possible. And one of those parameters that you would be adjusting would be a surface flux estimate. And you might have more than one of these. You might have, 5 or 6, depending on what you're doing. Or you could have a few hundred, just depends what you're doing. But yeah, when you adjust these parameters, some of them are going to be these surface flux estimates. And that's how you get an estimate of your flux, which is it's a rate of release or absorption per unit area. Cool. So look, one way that you can do this is by something called forward dispersion modeling. So what you would do, let's say you're interested in, what's happening at this point X, then you would identify locations nearby that you think are sources of methane, so sources of emission. And then you would use your atmospheric transport model to basically model the dispersion from each of those locations. And then as they pass over X, you look at the observed concentration that you've taken, so the measurement that you've actually taken from the real world, and you match up your modeled estimate, and that's how you estimate your flux. The only issue with that though is hopefully you can see by the time we actually get to X, the dispersion is all kind of jumbled together. You can't really see exactly what came from which location. So it's really hard to then go back and say, well, this much methane came from this location and this much came from this one, etc. So it's a little bit limited like that in what we're trying to do. So the other thing that you can do is you can actually start at this X that you're interested in and work backwards in time and follow that dispersion backwards. And what happens then is instead of this concentration here, this quantity here, it's no longer a concentration. It's actually something called a sensitivity of the measurements that you've taken here to the flux that's going on basically at every point on this map. So then you can say, well, there's a really high sensitivity over here, so there must be something going on here, etc. Okay, so a little bit of maths to put that together. There's not much maths in this talk, but we need a bit. So we're going to consider a k-dimensional spatial grid. We're just going to call that DG, and we're going to label the lower left corner of each of those grid cells as SK. And then we're going to define this process here, YM, to be a spatio-temporal mole fraction process, and YF is going to be a spatial flux process. And then if you've got a collection of space-time points, W1 to Wn, so these would be like a physical location and a point in time. Then you're going to consider the linear relationship. Ym is BYF plus epsilon, where Ym is that mole fraction process evaluated at each of these W's. YF is the flux evaluated at each SK, so at each square on our grid. And then this matrix B is a linear mapping that gets us between the mole fraction and the flux. And this is what we obtain using an atmospheric transport model. And these epsilon terms are just Gaussian error terms that capture measurement and numerical model error. Okay, so that matrix B, the ith row of that we're going to denote as BI, and that describes a cumulative 30-day sensitivity of the ith entry in Ym to the flux over that whole grid at the ith time point. So you pick a time point and you pick a space-time location, and then you look at the sensitivity of that space-time location, so the measurement that you took there, to the flux over that whole grid at that particular time point. Yeah, so then each BI, essentially it ends up being like this cumulative 30-day sensitivity over the whole grid, and it ends up looking like a plume. So we're going to refer to it as a plume, and we obtain this from an atmospheric transport model, as I said, and often that atmospheric transport model is something called a Lagrangian particle dispersion model. Okay, so this is it's from that simulation I showed before, that backward in time simulation. But what I've done is I've just summed up everything over the 30 days, and this is how you get that plume. And this is what we're going to focus on from here on out. Okay, so when you're doing a flux inversion, particularly over like a large area or a large time scale, or you want high resolution, etc., you need to run that Lagrangian particle model for every single real measurement that you take. And this is often, tens or hundreds of thousands. It's, huge numbers. And running these simulations using an LPDM can take quite a long time. Just to give you like some idea, depending on the resolution you set and some other simulation parameters, one run can take between like 10 minutes and 2 hours. So you can imagine if you're doing even like 10,000 measurements, you need to do 10,000 runs. If they take 2 hours each, it's going to take you forever. And this means that often when people are doing flux inversion, they either reduce the resolution of what they're looking at, or they reduce the time frame, or they reduce the number of particles that they actually use to run their simulations, etc., all to bring the time that it takes down. So we thought, can we build a surrogate model which can emulate what that LPDM would produce? So instead of running the LPDM every single time, can we build a faster model that still gives us what the LPDM would give us? And this idea has been considered before, but in a little bit of a different setting. So in the past, it's been proposed that you could build a model which would approximate an instantaneous output from the Lagrangian model. So this would be like a single value at a single grid cell, one point in time, And particularly, this has always been from forward dispersion from just one source that you know. And that source, to make it a bit easier, is usually something that is not affected by other things going on around it. So for example, if you have a volcano erupt and you're modeling the volcanic ash, it's not going to be affected, hopefully, by like another volcano. It's just going to be that one. And the way that they have done this in the past is they just take all the parameters that the Lagrangian model involves. They just take like an important subset of that and get an approximation that way, which is fine. It totally works for what they're doing. But for us, measurements of methane, like they're not just going to kind of float along in the atmosphere and not be affected by other things, because there's methane sources everywhere. So what can happen is you have some methane that comes out of this factory and it's sort of moving along in the atmosphere, and then there's some methane that comes from another factory, and then they get together, and then it's all sort of complicated. So you can't just sort of follow it nicely like that. And the other thing is that we're interested in these aggregated sensitivities over 30 days, which also makes it a bit harder to like just emulate instantaneous outputs from the Lagrangian model, because you're not really going to save yourself much time. So instead of focusing on the inputs of the Lagrangian model, we're going to shift our focus to the outputs, which are the plumes themselves. And we're going to say, well, can we take information from the plumes and try to build new plumes based on that, rather than trying to involve parameters of the model to start with. So to see, like why we thought we could do this, if you have a look at this animation, you can see that over time, these plumes are quite correlated, both in space and time. So this is over the UK, by the way. We've just got 4 locations over the UK, and we've done these Lagrangian particle model simulations every 2 hours. So basically, you would do a simulation at, 4 p.m. and then you'd run that simulation for 30 days, and then you'd sum all that up and you get your plumes. And then at 6 p.m. you do another simulation for 30 days, sum all that up, etc. So you can see why it takes a long time. But yeah, basically the idea is like, if this one wasn't here, could we use like the spatio-temporal information and the structural information as well from these other 3 plumes? Could we use this to basically predict what this one would look like? And hopefully you can see that that is quite reasonable from this example. Cool. So to do this, we split our approach down into 2 main components. The first was what we call feature extraction. So instead of trying to sort of emulate the sensitivity at every single grid cell over the grid, because that's not really going to save you any time, what we do is say, well, can we like extract important features from the plumes? So important features about the way they look, their direction, etc., and their sort of intensity. Can we extract that? And when we do this, think about it as like reducing the dimension down, because we go from, say 4,000 grid cells down to maybe 20, for example, in our work. And to do this, we consider 2 different methods for dimension reduction. So we use empirical orthogonal functions, which, if you haven't heard of those, they're like principal component analysis. It's the spatio-temporal equivalent of that. And we also went a bit crazy and used a convolutional variational autoencoder, which was really cool. So that's our first piece. So can we reduce the dimension down? And then once we've done that, on that reduced space, if we have a new spatio-temporal location, so we say, okay, I want a plume at this new location, can we use the information from the features of plumes that we already know to emulate the features of a plume at that new spatio-temporal location? And to keep track of the uncertainty while we do this, we use Gaussian process emulators because that will give us a variance measure as well, or a standard error. Cool. So for our first feature extraction method, we did the empirical orthogonal functions, or EOFs. And to do this, it's fairly straightforward. You're going to compute a singular value decomposition of your plumes. So take that matrix B, break it down into these three matrices, where U is a collection of coefficients. D is I think it's actually the square root of the eigenvalues. I should have fixed that. And V is all the eigenvectors. And the way that these are ordered is such that the first ones capture the most variability in the plumes. So the first eigenvalue and eigenvector, that might capture 60% of the variability. It probably doesn't. That's a massive overestimate. And then the second one will capture something less than 60%, and the third one will capture something less than that, et cetera, et cetera. So as you go along, you're capturing less and less variability. So what you can do is actually subset those eigenvalues and eigenvectors and still get quite a reasonable reconstruction of your plumes, because you're only losing a little bit of the information by cutting out, the end plumes. So what we do is we keep the first 20 and try to do, reconstructions from that and see what they look like. Okay, and then the really cool one. So with the convolutional variational autoencoder, or the CVAE, essentially it's a lot of things, but we have our inputs. So these will be the images of the plumes. We're going to stick them into an encoder, and this is just made up of convolutional and then pooling layers. So the convolutional layer captures the information, and then the pooling layer reduces the size down, and then you do convolution one again, pooling layer all the way down until it's small enough that you're happy with it. And then we basically flatten it out, and then we basically sort of map onto a mean and a log variance of a Gaussian distribution. And then we draw values from that distribution, and we send those back through a decoder, it's sort of just like the mirror image of this. It just goes back the other way. And out come, hopefully, approximate reconstructions of what you put in at the other end. Now, the cool thing about this is, because we're mapping onto a mean and a log variance of a distribution, it means that in this space here, you have a lot more ability to actually generate things, because you don't have sort of this really disjoint space where, for example, in an autoencoder, if you've heard of that before, your inputs would just get mapped to specific values, and any values in between those two are like completely meaningless if you put them through the decoder, because there's no necessity for them to make sense. Like, there's no necessity for you to need to like interpolate between them or anything. But if you put distributions down, then interpolating between values in this distribution actually makes sense. Okay, so what I've shown here, it just describes a CVAE with a one-dimensional latent space here. So we call this the latent space. However, in our work, we use 20 dimensions, but how do you draw a 20-dimensional Gaussian distribution? So I didn't do that. Yeah, now the variational part, so that it's literally just from variational base, because what we do is we treat this decoder here, we treat it as our likelihood. So we say, given the parameters, or the current values of the parameters, what do our reconstructions look like? And then we set a prior on this latent space, which is just a standard Gaussian. You can change it, but we just use the standard Gaussian. And then the encoder acts as your posterior distribution. So we basically update the values of our parameters given given the plume images. Yeah, so basically when you train this, you're just updating this posterior distribution, which is kind of cool. Yeah, so during that training, we're interested in maximizing our marginal likelihood. So this guy here. However, this is, intractable. We can't do that directly. So what we do instead is derive a lower bound for this, and then we just go and maximize that lower bound. So a little bit of maths later, you end up with this expression down here. So we have an expectation over the log likelihood. And then we subtract off something called a KL divergence. Now this guy here, all it does is measures the similarity between the prior that we set and the posterior. And the reason that we want that, we want them to stay close together, is that this should be a plus, I think. Sorry about that. We want them to stay close together so that we can actually also interpolate between the Gaussian distributions as well. So we want the space between each of these little Gaussian distributions on the latent space. We want that to make sense as well, because our goal at the end of all this is to generate new plumes. So we want to be able to generate from our latent space. Okay, if we assume IID reconstruction errors, maximizing our marginal likelihood is equivalent to, oh, there's the plus. That one's right. That's the plus. Sorry, my apologies. Yeah, so it's, if we maximize the log of our marginal likelihood, it's equivalent to minimizing this guy here. And I've basically already said all of this, but yeah, P of UI is our prior. Q of UI given BI is our approximation to the posterior distribution, because we don't know this exactly, so we approximate it. And the KL divergence is called a Kullback-Leibler divergence, and this is what measures that similarity. Okay, so all we did to start with is we used both of our dimension reduction techniques, reduced the dimension down, and then we just tried to reconstruct the plumes that we already had. So we used 20,000 plumes obtained from an LPDM called the Flexible Particle Dispersion Model, or FlexPart. So we stuck them in, reduced the dimension down, and then tried to reproduce them, and just to see what we were actually capable of doing before we try and do any emulation. So this guy here, this is the true plume. This is what it looks like as given by FlexPart. And then when we did it with the EOFs, this is what we got. And when we did it with the CVAE, this is what we got. And we've got some mean squared errors up here as well. So look, the biggest takeaway for me from this is that the CVAE actually managed to capture that tail a bit better than the EOFs did. Possibly if you used more EOFs, you would get more of that tail, but the more EOFs you use, the higher your dimension is, the slower your emulation is going to be. So at some point you've got to draw the line. But it was really cool that the CVAE managed to capture that. Okay, so then we moved on and we said, okay, yes, we have the ability to reduce down and reconstruct our plumes. Can we emulate new ones now? So the really cool thing is that both of those feature extraction methods, they're actually independent of the LPDM. So just because I used FlexPart plumes doesn't mean I now for the rest of my life have to use FlexPart plumes to reduce the dimension. So what we did is we actually took then a whole bunch of plumes from a different LPDM, just because we could, called name. And we said, okay, let's try and emulate name plumes just for fun. Okay, so with the EOF deconstruction, we build spatio-temporal emulators to construct new vectors of those coefficients. And then we multiply those by existing eigenvalues and eigenvectors, and that gets our predicted plumes. So the coefficients, they would be entries in that matrix U when we did that singular value decomposition. And this approach is quite common. It's nothing new to this work. But for the CVAE, what we do is we use our emulators to construct new variables on that latent space. So we're basically, like trying to interpolate between the values on that latent space. And to our knowledge, this application of a variational autoencoder is new, which is cool. So just quickly, under a Gaussian process, if I'm trying to model the jth feature for a plume at some new location W, that's going to follow a Gaussian distribution with the following mean and variance, where this uj in the square brackets, this represents the jth feature of the plumes at each of those known locations that I have. And our covariance matrix is, it's just a squared exponential, but we gave it a spatial and a temporal component to it. So if you have two spatio-temporal locations, WA and WB, then the covariance value, so one of these entries in this covariance matrix, is just going to be the distance between the spatial components of WA and WB and the distance between the temporals. And we also have a spatial length scale and a temporal length scale, and they are you have one of these for each feature, and each of those, so the length scales and this variance value out the front too, each of these we fit via maximum likelihood estimation. Okay, so what did we do? So we took that set of named plumes. We had about 5,700, and we took out every second one of them. And then we said, can we emulate the ones we took away with the ones that we kept? And something I should have mentioned, which I didn't way before. So when I did this, the plumes, on their own weren't just nicely sort of facing out from zero and centered on zero and everything. I actually transformed the origin to zero for each of the plumes. And then I actually also rotated them so that at least their departure angle was the x-axis. And the reason I did this was just to reduce the amount of variability that my feature extraction methods had to capture, because if you remove some of the direction, you're able to capture other information, so you can get more work. So because we trained those feature extraction methods on rotated plumes, because I rotated everything, so had its departure angle as the x-axis, we had to rotate the name ones too, which is totally fine. It just meant that we had to also then emulate an angle, like a true departure angle of the plume, so that we could rotate it back to that angle. And that ended up being actually quite not straightforward to do. It was quite difficult to do for a while. What we ended up doing is fitting additional Gaussian process emulators to the horizontal and vertical components of the departure angles, and then we just stuck them straight into a rotation matrix, and that's how we got the rotation. Okay, so results, pretty pictures. So here's our true plume, and this is unrotated, back on the original space. Everything's normal. We're back on the UK. So these reconstructions, they're based on me doing the Gaussian process emulation, and when you do that, you end up with a mean and a variance for a Gaussian distribution for each feature. And then I drew 100 samples from each of those distributions, and for each of those sets of features, I then constructed the plume, rotated it back. So then I had sort of 100 plumes back on the original space, and then I took the mean over the grid cells and also the standard deviation to get these uncertainty plumes down here. So here I have the reconstruction based on those 100 100 Monte Carlo samples for the EOF dimension reduction. And then here I have it as well for the CVAE, and our mean squared errors up there, of course. And down here, these are my uncertainty plumes. So you can see, like in both cases, they actually did quite well. But the cool thing is the CVAE, the uncertainty is a lot narrower. So you can really see that this guy here, you know, did a better job of the emulation more often. Whereas you have, you know, a lot more uncertainty here, which is really cool. Another example, so the true one is here again, EOF, CVAE, uncertainties. So I think these ones are pretty similar. And another one again. Again, the cool thing here is that the true one has this bit of a curve in it, and the EOF sort of missed that curve, but the CVAE got it, which is really cool because, you know, you have to remember this plume did not get put into the CVAE to reduce the dimension down. All we did was take other plumes and use the information from those to predict the shape of this one. And the same deal for the EOFs, like the information from this exact plume was not given to these methods, which is really cool. So yeah, a few numbers now. So these guys here are basically a sum of all the mean squared errors. So for every plume that we emulated with the EOFs or the CVAE, for the training, so this is where we just put the plumes in and basically observed whether we could reconstruct them. So to do that, these are our like the sum of all the mean squared errors. And the CVAE is a lot lower than the EOF one, which is cool again. And that's what we saw when we actually looked at the reconstructions. We saw that the CVAE did a fair bit better. And then when we got to the emulation, again, the CVAE still did better, but the EOFs actually did quite well as well at emulating those name plumes, which is cool. And then down here, I just have a histogram of the normalized errors. So they're calculated as, so for each plume, you'd take the EOF mean squared error minus the CVAE mean squared error, divide it by the EOF mean squared error, which means that having more positive values like we do, that means that the CVAE has done better based on our metric most of the time. Okay, so what have we done? We have trained 2 feature extraction methods using plumes from FlexPart. One of those feature extraction methods was with EOFs and the other one was with our CVAE. And when we used the CVAE, we observed marginal improvement over using the EOFs when we tried to actually emulate some plumes. And the really cool thing is that once you set those length scales and variance parameters, and actually, even if you don't set them, like even if you have to do the maximum likelihood estimation, the time taken to get those emulated plumes, which was about 2,800, is at least 5 times faster than if the LPDM was used itself. If you don't have to do the maximum likelihood estimation, it's even faster than that, which is cool. And yeah, so the biggest thing is that this has the potential to save atmospheric chemists quite a large amount of time. And it also means that now we could, you know, run larger scale flux inversions at like a finer resolution, which is really cool. And that's something that's been a little bit limiting before. Okay, and where are we planning to go from here? Well, what we'd like to do is actually, you know, try our emulated plumes in a flux inversion just to see if they still hold enough information that we can get meaningful fluxes out, because that would be really cool. And that's sort of the aim. And the other thing that this has the potential to do is actually, we could extend this methodology onto more complicated plumes. So you have like plumes that are averaged down an entire atmospheric column, which are, you know, there's a lot more information in those, but we'd love to try and get our methodology to work on those plumes as well. And I think that's it. Yeah. Cool.
Thank you so much, Laura. I think you can hear me again, right?
Yep, I can.
Yeah, what a wonderful talk. Are there any questions in the room before I start rattling off? No, or in the audience, if anyone wants to ask a question, just raise your hand and unmute yourself. I was wondering the difference between, I guess, your training and your testing. Was the reason you did it on the name, I guess, model, because it was like more akin to like an out of sample kind of validation, or out of sample test? Was that the reason? I
think the main reason that we did it was just so that people didn't think, you know, because you train it with FlexPart, you then have to use FlexPart for the rest of your life. Like we definitely could have done it with more FlexPart plumes, but we just thought, like, because we don't have to, and we had access to a bunch of name plumes as well, you know, we just thought, let's just do that and show that it doesn't matter where you get the plumes from. You sort of just train the model once for a particular scenario, and then, you know, if I go back and I make, you know, another 10,000 plumes over England for that same roughly time period, I can just use the same emulator again. Like I don't need to train it again.
So in that sense, it's like amortized. Once you've done the training once, it can be applied within reason to similar plume.
Yeah.
Oh, that's great.
Yeah. Yeah, it's really cool. The only thing we noticed was like, because we were quite ambitious at the start, as you always are. And we tried to emulate stuff over Brazil. And Brazil is very mountainy compared to the UK. And so you can't use a model that you train over the UK to emulate something over Brazil, because it's not fair. It doesn't have that information. So if you went to a totally different terrain, you'd need to train it again. But if you wanted to emulate over where else is flat, like, I don't know, certain parts of Australia or whatever, instead of the UK, like, it would probably still work. Yeah.
And then another question I had was, do you know if the convolutional variational autoencoders, I think I got the name right, do you know if they've been used in approximate Bayesian computing before to emulate the simulation of the new data set that you use in ABC?
They've definitely been used to generate before, like that's not new to us. But I think most of the time they just get used to generate fun things. Like, I don't know if you've ever seen those images of people that are like half men, half women and stuff.
Yeah.
But that's from a CVAE. Basically, they just sort of, you know, interpolate between man and woman on the latent space and then send that through the decoder. And because they're distributions, you get like a sensible interpolation out the other end. But yeah, they have been used to generate other things, but I don't think they've been used the same way we've done it. But I could be wrong now because I haven't checked for a few months.
Yeah, it seems like there's a lot of machinery around your use of them in order to make sure they work for your context, which is very important to make sure that they're doing the best that they can when you've got all this like correlation across space and time, right?
Yeah.
To account all of that. Did you find them easy to implement and use, like from a programming and implementation perspective?
Yeah, that's a good question. So there's a bit of a hurdle when you first start learning. So I used Keras and TensorFlow. Yeah, like the first time you see those packages, it's a bit of a hurdle, but I think once you work out how they work, it's actually really easy to build the models. It's just building the right one can take some time because there's no like there's no sort of flow chart that tells you what you should do if it doesn't work, or, you know, which thing you should change. So you can sit there for ages trying to fiddle with it. Like, I think it took me maybe 6 months to get the model that we use now. But like, it's fun. It's kind of fun fiddling with it. And you do get better. And I think, you know, now, like, I'm not really scared to use those packages at all. So I think it's easy once you get your head around it.
Yeah. Yeah, a bit daunting if you haven't used them before, I guess. Were there any questions online or in person that I want to
think there's a message in the chat.
I think someone was saying, thanks for the great
talk. That's okay. That's easy.
Yeah. To answer your question, yes. It was a great talk. All right, well then, if everyone can join me in thanking Laura online and in person. It was great to have you. Thanks so much.
Cool, no worries at all.